Okay, so thank you very much. I'm very pleased to be here to be able to present the work to you. I hope that everybody was able to attend the very interesting talks yesterday. And I'm kind of building on or suggesting a slightly different way of using the data from the ASV. So if I just very quickly talk about the site that I work at. As mentioned, I moved to Gothenburg about 13 years ago. That's on the west coast of Sweden. So you can see on the map there, Northern Europe, cold winters, long summers, and very beautiful environment with lots of islands and forests and lakes and things like that. So nice place to live. It's one of the centres of AstraZeneca's research, where we're involved in cardiovascular, respiratory, cancer and rare diseases, and the work on the site covers the entire life cycle of drug discovery and development. So just if I talk about what we want to do with why do we want an automated structure verification system. So the kind of context that they're working in is where we are looking at hundreds of compounds per week, and an ever increasing amount of automated chemistry, and smaller amounts of material as well. So the question is, like, how do us analytical chemists, how do the chemists keep up with the data, especially going forwards? And it's going to be a bigger challenge for us. So we need more automated systems. I guess initially they save time for the analysts and the chemists, but ultimately you'd like the systems to be able to make decisions for you. So some assumptions then. So I'm assuming we're using mass spec so that we know that the molecular formula of what we've made is correct. So actually what we want to do then is know that we've got the right structural isomer. Another nice to have thing with a system is that it knows when it doesn't know. So in other words, if you can say, if a system says, yes, it's right, no, it's wrong, or I'm not sure about this one, because then at least you could use the I don't knows to collect more data or human interpretation or some other route. So then the key question is, how well does the ASV software work? And my answer to that is it depends. So we want right compounds to pass and wrong compounds to fail, so low numbers of false negatives, false positives. And the results you get are very strongly dependent on the test compounds that you use. So I have to say I'm one of the people that thinks the basic use, the ASV as it stands today is not good at deciding whether a compound is right or wrong. So there's too many false positives and false negatives, especially when you're trying to look at very similar compounds as like chemists might make. So reaction products, they're by the nature going to be very similar to each other. They're not easy to distinguish between, and that just making a pass or decision, a pass or fail decision on the basis of the ASV results today is very difficult. But I have better news. I say I have a slightly different way that we can use the data, which I'm going to talk about. So this is what I'm going to talk about. I'm going to talk about how we set up a database of a data set of very similar compounds to test the ASV performance. I'll explain a bit about something called receiver operating characteristic curves, which is how you can display the performance of a large amount of data, and then say, are we actually asking the best question? So then I'll say, introduced to a different way of looking at the data where we're actually comparing the scores of the similar compounds. I'll talk a bit about a possible workflow, and then I'll just finish talking about other data that can be useful in this for us as well. So we put together a data set of 42 drug-like compounds with average molecular weight about 300, 2 to 3 decoys for each. So two or three compounds of the same molecular weight where we've made only one chain between them. So pretty similar, but the kind of things you might like to distinguish between. So in total, we had 98 match decoys. And then the data was collected under realistic conditions. So, some signal to noise issues, some impurity, minor impurities present, that kind of thing. So here's just an example. I'm just going to show 4 examples of the kind of typical things. So if you look at the top row, these are all the correct compounds. And then you see the decoys we created. So I think you'll agree some of them are pretty difficult, but they could well be realistic. So for example, here we're moving the hydroxyl around the ring. Here we've moved the double bond. Here is a geometric isomer where we're pointing the double bond, E and Z isomers. Here's diastereoisomers. Here we've swapped a couple of groups. Again, difficult diastereoisomer. Here we've swapped a couple of groups as well. So I think you can agree they're not easy, but also they're probably quite typical of the kind of things that we would like to distinguish. So if we put these into the ACD program, I just, for a start, I'm just going to show you the proton ASV scores with automated peak picking. You see we get these scores out. So using the ASV in the traditional way, we have to decide upon a score, and we're saying above that score it's a pass, below that score it's a fail. So let's just, for the sake of argument, choose 0.5 as that. So you see now we have, if we look at what along the top row, where they're all correct, we see we only have a 50% pass rate. 2 of them score quite low. And then if we look along the decoys, you'll see that although 5 out of 8, I think, have failed, we still have a number that get high scores and that would pass, that we couldn't kind of distinguish between. So that's just 4 examples out of the 40 odd that he had. So how do we plot all that data in the way that we can make sense of? So the way you can do that is called a receiver operating characteristic, where we're plotting the true positive rate against the false positive rate as a function of this threshold that we pick. So if we had a completely random process, we'd have a line like this along the diagonal. So how does it look like with the proton? So these are the results that came out of the proton data set that I just showed you. So it's clearly doing significantly better than the random process, but where we really want to be is up here, where we've got 100% true positive, 0% false positive. And if we kind of want a measure of what the performance is, we can look at the area that's under the curve. So a perfect system would enclose this area in green, and where we're actually enclosing is the area in blue. And if we look at the numbers for that, it's about 33%. So just to remind you, a random process would score 0 on that. So it's doing something, but also there's quite a bit that still needs to be resolved, or still needs to be improved upon. So how does HSQC and carbon look on the same way? So HSQC is somewhat better than proton. Carbon, I'd say, is markedly better. Still, I think leaves something to be desired. So, for example, if we're using carbon, I think arguably the X marks the best performance spot but we're still getting a true positive rate of 0.74. So that's about 25% of false positive and about 25%. So 25% of false positive, 25% of false negative. And then if we look at how well they're performing, so carbon gets up to 50%, but that's still kind of 50% room for improvement. So let me just say about how we can look at the data in a different way. And I'm going to introduce that by thinking about, what is our day-to-day kind of problem in the lab, or what does it look like? So I'm going to think about two chemists. So the first chemist maybe comes up to you and they said, well, I just did some reaction, but I don't remember what it was, and I made something. Can you tell me what it is? Now, I think if I heard that, my heart would sink. Maybe it could have a go at telling them what it is, but really there's no context to the problem. So, they don't even remember what materials they put into the reaction or how it was made. So you might be able to get some way to solving that, but it's certainly not an easy problem. So think about another chemist who has done their reaction. They get 3 products out, and they ask you which product is which. Now, without even knowing what they've done, I'd be pretty confident that I can solve that fairly easily with 1 or 2 experiments. So what I say is that what we're asking ASV to do is something like Chemist 1. So, we're asking it to tell you if a compound is right or wrong, with very little context to that. And that is a very difficult problem to solve. So I'm not saying, certainly there's room for software to improve, but I think actually we're not asking the best question. So Chemist 2, that's a much more likely for what we do. We know what reaction has gone on, we know what products might come out, and we just want to distinguish between them. So how can we, if we now use that concept with the same data that I already told you, so now we're looking not at the absolute scores, but now we're looking at the difference in the scores and how they compare. So for example, this decoy scores a lot lower than the correct answer. Here we've got 3 examples that score 0, so they're exactly the same, but at least we know that we can't tell the difference between these. And then here we have some more examples that score lower, maybe sometimes only by a small margin. Here we have one that scores higher, although it's wrong, but only again by a very, very small amount. So how could we again plot all that information on so that we can see it all at once, see how well the method performs? So what we came up with is this structure classification characteristic. So we're plotting the classification rate, in other words, how many pairs of compounds can we distinguish, and then the correct classification rate. So how many times do we get it right? And where we want to be is up here. Where we want to be is up here, where the green circle is. So we're classifying everything and we're getting everything correct. And random would be this line here. So if we then put the proton, the HSQC, and the carbon onto a line like this, we get plots that look like this. And if we, again, we can look at the area under the curve compared to the total area, and we can get a view of how well this is performing as a method. So again, we've got proton at 79% up to carbon at 95%. So if you remember the comparative figures that I showed you before, proton is only 30%, up to carbon at 50%. So, as a method, this is not perfect, but it's performing considerably better than just taking a single compound. So that does come with compromises, of course. So if this doesn't make sense if you don't manage, if you need to close data sets. So in other words, if you haven't managed to predict what's actually been made, then you're going to get a meaningless result out of it. So it does come with a compromise. I'm not saying this is the only thing that we should ever do, but I think it's a step forwards. So how does that fit into a whole workflow then? So the idea is, we have the reagents, they go into reaction prediction software, which predicts possible products out of it. This then goes into the ASV software. We're collecting data on that, Proton, HSQC, and COSY, and then we can rank the products. The vision, at least at the start, is that if we find something that we think fits the data better, then we can flag that to the chemist. So, as I said, I don't think this is definitely, I think, a start and something very interesting, but it's probably not everything that you would want to do. So here are some suggestions about things that ways to improve that. So I think, most people would think that probably if we look at mass spec fragmentation, that's probably going to give some useful information extra. We might want to, as an additional step, use structures that have been suggested from generative AI based on the data. That might resolve problems where, say, the chemist got the starting material wrong, or we've got a completely unprecedented reaction product coming out. What I want to talk about in the last few slides that I'm particularly excited about is the role of infrared in this. So that's going to be my last few slides to finish this talk. So this is based on master's project and now PhD students that we have, Lena and Benji, who work Benji works with Professor Jonathan Goodman at the University of Cambridge. Some of this work is published in the preprint here on ResearchSquare, which you can find. So the idea is having an experimental infrared spectrum and then comparing it to a calculated infrared spectrum. And then there's an alignment algorithm that basically tells you how well do they match. And just like the ASV software, you get a score from 0 to 1. So how well, and again, the way we're using this is looking at the differences in the scores. So against the different products, how well does infrared do at ranking the products? So if we put that information onto the graph that I showed you earlier, we get this result. So it's proton, HSQ carbon, just the same as I showed you before, but now there's infrared on there. So I don't know if people are that familiar with infrared. Maybe you're pretty shocked or surprised at just how well it does. I mean, we certainly were. So let me just spell it out for you. So actually, this kind of simple way of just comparing the infrared spectra is actually performing better than the proton ASV. I should say the proton ASV is with automated peak picking. If you do manual peak picking, you can actually get the proton to be a little bit better or maybe the same as the infrared. But the point is this infrared matching algorithm doesn't need any peak picking at all. And also, again, infrared is pretty sensitive, so you can probably collect the infrared spectrum on about an order of magnitude less material than you can collect a proton spectrum. So does that mean the end of NMR? Absolutely not, because I said infrared does well, but it doesn't do well enough either. So what happens if we combine the data? So then I've added the green line in here, and I've chosen to show you the results from HSQC plus infrared because I think that's where the most likely thing that we would want to do. So combining HSQC and infrared actually brings you right up here with an area under the curve 98%. So we're getting closer and closer to 100% or a system that we would we could use in full automation. I'm sure you're thinking, what happens if you can combine infrared with carbon or HSQC? You do see an improvement as well. So actually, infrared plus carbon does even a little bit better than the line I've shown you there. But I think we also need to think about what data can we collect in a reasonable and quick time. So just some conclusions then. I think it's an exciting time for structure verification. I think there's a lot of new approaches, a lot of new ways of using the data. And so I think there's going to be big developments in the next few years. I think we need to be realistic about the question that we ask, giving a proton spectrum and saying, is this right or wrong? That's a pretty difficult thing to expect any piece of software to answer and get it right 100% of the time. I said we're foolish if we don't make use of all the information available to us. I guess what I'm primarily meaning there is synthesis information. So, the starting materials that went into the synthesis should certainly be important. I think the role of infrared looks very exciting. We're looking at ways of collecting infrared high throughput, highly automated ways. And as I say, I think the future is likely to be a mix of different approaches. So not just one bit of software, one bit of data, but putting lots of different softwares and data together to get an answer. So my final slide, I mustn't forget to thank all the people that have been in the past and are still involved in this project within and outside AstraZeneca. Okay, thank you very much for your attention.